Today, we begin a topic that every chemistry student fears and dreads. Welcome to Dimensional Analysis with mole ratios, where we divide one mole by another mole in the middle of a beautiful long conversion dimensional analysis setup to get from grams of one chemical to grams of another chemical. So, by the end of this video, you should be able to use said mole ratios in order to convert grams of any one chemical to grams of any other chemical. Let's waddle right in, shall we? As with any good lesson, let's start with a review before we jump into this new concept of mole ratios. So first, let's write this following chemical reaction using the actual symbols for it, so converting the words to the chemistry format from the periodic table. Balance that equation, including state symbols, figuring out what type of reaction it is, and then calculating the molar mass of the product. So, first things first, we have magnesium reacts with oxygen to form what? Let's start with magnesium, that's Mg, and that's typically a solid, it's a metal, so that's my state symbol right there, plus oxygen, and oxygen is a diatomic molecule, so we would never just write O, it's O2. It always comes in pairs, just like ladies going to the restroom. They go in pairs for safety. So we have O2, oxygen, and that is typically a gas. That's, you know what you're breathing, that oxygen. So typically in gas form. I don't recommend breathing liquid oxygen. Then those two react to form, what is our question mark? Well, we need to first figure out what type of reaction this is. If we look at our patterns for types of reactions, we see we have one thing with one other thing. Neither of those are compounds, so that certainly looks like a synthesis reaction, where we have two or more different kinds of atoms that can come together to form one thing. In this case, we would be forming MgO. And when we pair those two together, we need to make sure that the charge is balanced. If we look at our periodic table, we see that oxygen has a -2 charge and magnesium has a +2 charge. So magnesium oxide, MgO, or if you flip it around, oh my gosh, is magnesium oxide product. What would be the state of this product? Well, if you had seen one of my previous videos where I did this reaction, I actually lit the magnesium ribbon on fire and it burned and created MgO, which is a supplement that you can actually purchase and ingest, you would find that that product is indeed a solid. That would be a solid product. We can also hypothesize this because MgO is an ionic bond and it's not in anything that was liquid to start with, so it's likely going to be a solid product at the end. And if you wanted to check out that reaction in real life, go ahead and click on the video linked in the description below for the types of reactions with demos. Now, if we balance this chemical reaction, we need to compare our product side to our reactant side. On the product side, we have 1 Mg. On the reactant side, we also have 1 Mg. Now, where it gets a little screwy is the fact that we have 1 O on the product side, but 2 oxygen atoms on the reactant side. So we need to balance this by playing with our coefficient value on the product side. And that would happen to be a 2 because we need 2 oxygens on the product side. So I'm going to put a 2 here. And then that fixes our oxygen problem, but messes with our magnesium, because now we have 2 magnesiums instead of 1 magnesium like we just did before. That's an easy fix. All we have to do is now put a 2 in front of the reactant side magnesium in order to balance that back out. And voila, we have a beautiful balanced equation. Now, in order to calculate the molar mass of magnesium oxide, our product, we need to look at our periodic table in order to add up the separate masses of magnesium and oxygen together. If you're looking at your periodic table, you'll see the small number underneath magnesium is 24.305. And the value below the oxygen is 16. So we need to add 24.305 plus 16. Yes, I did round that. It's typically 15.999, but I'm not going to torture myself. Now adding those two values together gives me 40.305 Now remember, we can't just send this number out into the streets all naked. We have to give it units, and that would be grams per mole. Another way that we write that is 40.305 grams per 1 mole. Those are equivalent ways to write this conversion factor of molar mass. Now, why did we do this quick review? Because these are the first essential steps before we even begin mole ratios. If you don't have this down pat yet, I recommend going back, practicing these, making sure you understand it efficiently before moving on to mole ratios, because that'll just complicate your life a little bit more if you don't know how to balance chemical equations or find molar masses. Without further ado, what is a mole ratio? What do you think a mole ratio is? Well, hopefully you remember from the past that a ratio is one number over another number. So a mole ratio would be a mole over a mole? Question mark? Just like the mullet ratio, you have business in the front, party in the back. What's your ratio of how much business versus party you have? Here we're going to have a ratio that, yes, is in fact going to have a mole over another mole value, but for two different chemicals. And we're going to use that as our bridge to cross from one chemical to another when we're converting and finding grams of one to grams of the other. So think about how we write ratios and how we've used our domino pieces in the past. We've always been able to flip a domino one way or the other. We could have grams per mole or mole per grams. You could have atoms or molecules per mole or 1 mole over atoms per molecule for Avogadro's number. We have different ways we can write those by flipping our domino pieces according to the use we need it for. So those are ways we can write this mole ratio, is one value over another, and we can flip that as we see fit, as long as the numbers are glued to the correct units. Where do you think we'd look to find those numbers then? Where are we going to find the mole ratio numbers? We, of course, have to look at our balanced chemical equation. Remember those coefficients that we can mess with in the front to balance the equation? Those are our mole numbers that we will use for our mole ratios. So yes, molar ratios, the entire reason why you should always be in the habit of checking to make sure your chemical equation is balanced first before you do any math ever. If you don't make sure your equation's balanced first, the rest of the math you do is essentially useless because you will get the answer wrong. From the quick review that we just did to start the video, what if we wanted to know how many grams of the magnesium oxide, the product that I mentioned, in the reaction that we could make? What if I took a certain amount of magnesium and lit it on fire so it would react with oxygen, and I wanted to know how much product, how much magnesium oxide could I yield, could I make from that reaction? This is the entire premise of chemistry and doing labs, for that matter, or experiments. We want to know how much product can we make from this. If you were trying to synthesize, let's say, biodiesel fuel from oil, that's something that I did a research paper on when I was back in college days, so long ago. When you want to synthesize something like that, you want to know how much biodiesel fuel could you make from a certain amount of oil. That's kind of important if you are the person trying to create a corporation or a business whose sole purpose would be, I don't know, generating biodiesel fuel. You'd have to know how much reactant, how much oil do you need in order to create the sellable product of biodiesel fuel on the market. So these calculations are very essential to literally all of the real world applications of chemistry. And herein we use our molar ratios. Before we jump into using that math with molar ratios, let's think about it in terms of something that's physical. Like me, there's one Mrs. Duckonta and 2 arms. Are those two quantities equal to each other? Could I say every time there's one Mrs. Duckonta, there's 2 arms? Yes, I mean, right now you could, but when I was younger, I almost lost my left arm. Fun side note here, because I broke it in Europe. And well, you know, in Europe, when I was 10 years old, they decided to cast my arm before it had time to swell all the way. So I almost lost my left arm. I was probably about an hour or 2 away from them having to just cut my arm off. So yes, right now, thankfully, one Mrs. Duckonta equals 2 arms and not just 1 arm. I'm very, very grateful for my arm still being here. So because of this fact, I could say that I can represent this equality or these quantities as such. I could say that 2 arms are equivalent to 1 Mrs. Duckonta, or 1 Mrs. Duckonta will always possess 2 arms. So this ratio is true no matter which way I write it. Likewise, when I take a chemical equation and replace that arrow, the reaction arrow, with an equal sign, I could say, okay, what about 2 Mgs, 2 magnesiums, reacting with 1 oxygen? Is that equivalent to 2 MgOs? Are those quantities equal to each other? Everything on the reactant side equal to what's on the product side? Hopefully you're saying yes, emphatically, because the law of conservation of mass would dictate that whatever you start with, you have to end with. So of course the reactant side has to equal the product side. It has to be. There's literally no way we're going to break that law of conservation of mass. Therefore, we could say for every 1 oxygen, there are 2 magnesium oxides in this particular reaction. So we could also represent that as a ratio. We could say 2 magnesium oxide is equivalent to 1 oxygen, just like 2 arms for 1 Mrs. Duckonta. Or we could flip that domino piece and it would still be the same thing. We could say 1 oxygen for 2 magnesium oxide, just like 1 Mrs. Duckonta, 2 arms, yet again, because those 2 sides of the reaction are equal to each other. Now that's what I mean by using the coefficient values from your balanced chemical equation for your mole ratios. We can take those values in the front and put one over another to go from, say, oxygen to magnesium oxide in a calculation problem. So then a mole ratio by definition is taking the coefficient numbers in front of your balanced chemical equation from whatever chemical they're in that you're interested in and putting one on top of another. In other words, we have 2 moles of magnesium reacting with 1 mole of oxygen, creating 2 moles of magnesium oxide. And all of those ratios are equivalent to one another in this context. And you already know that a ratio is any number divided by another number, i.e. a fraction. Therefore, a mole ratio, by definition, would have to be the coefficient number from the balanced equation divided by another coefficient number in the balanced equation. Understanding checkpoint, understanding checkpoint. Before we move farther, make sure you understand. How many moles of magnesium do you need to make 2 moles of magnesium oxide? So how many moles of magnesium do I need to make 2 moles of magnesium oxide? Hopefully you're seeing I need 2 moles of magnesium to make 2 moles of magnesium oxide. And how many moles of oxygen do you need to make 2 moles of magnesium oxide? So how many moles of oxygen to make 2 moles of magnesium oxide? Again, hopefully you're seeing you need 1 mole of oxygen to make 2 moles of magnesium oxide. Let's make sure you understand how to write them as a ratio, as our fraction domino piece. How many moles of magnesium are there 2 moles of magnesium oxide? Hopefully you're seeing we would take the magnesium value, 2 mgs, and put that over the 2 MgOs. When we do that, we can reduce because there's 2 over 2. Now you could have just as equally said 2 mole magnesium per every 2 mole MgO. And that would be the same exact thing as writing 1 to 1. Again, this just reduces to 1 as I have written here because 2 divided by 2 is 1. You can keep it as 2 over 2 if you're more comfortable with that. How many moles of oxygen are there to moles of magnesium oxide? Just as before, we're going to take the moles of oxygen and put that over our moles of magnesium oxide. In this case, our fraction would look like 1 mole O2 over 2 mole MgO. Notice that I have these labeled both times. I don't want to just write 1 mole over 2 mole because I have no idea what chemical that's associated with. This is where the labeling is absolutely crucial. If you do not label here for the chemical that you're looking at, you will probably get the answer incorrect by the time you're done calculating and doing all of that hard work to get there. Now, we started this graphic organizer in a past video when we were converting grams to atoms to moles and moles to atoms to grams and so on and so forth. And we used Avogadro's number here which is the 6.02 times 10 to the 23rd, atoms or molecules per mole. And we used molar mass here, which is our grams per mole, which we found from the periodic table anytime we want to add up or convert from moles to mass or mass to moles. Well, if we need to go from mole to mole up here, we're going to use our mole ratio. And just as a reminder, where do we find that mole ratio? The coefficient numbers taken from the balanced chemical equation. This is what we must do anytime we're going from grams of one chemical to grams of another. So for example, we have grams of, say, oxygen from our quick review problem we started with. We would have to go to moles of the oxygen using the mole ratio, then go back down to figure out the mass of our product, MgO, if we were starting with O2 going to MgO. Again, just a fair warning. Do not skimp on the labeling. I can't tell you how many times students would get this wrong just because they would flip-flop the mole ratio and get the entire answer incorrect in a lab report or otherwise on a test. Don't skimp on the labeling. The labeling is literally the only thing that will save you at this point in chemistry, especially when your mole ratios are not the same value, reducing down to 1. It will entirely skew your answer. Okay, so you're probably wondering, holy crap, Mrs. Duckonta, when are you going to finally show us the example dimensional analysis? Let us begin. As always, let's read our question and then figure out what we need to do. If we used 5 grams of magnesium, so magnesium ribbon, I cut a piece, it was 5 grams of it. How many grams of magnesium oxide, our product, could we make? Let's note first that I'm given 5 grams of magnesium. I'm given 5 grams of my reactant, and I'm asked for something different, grams of magnesium oxide, which is a completely different chemical. If we're going from one thing to something completely different, that's a dead giveaway that we need a magical line to freedom. And in this magical line to freedom, I have my equal sign, a space for my answer, and my goal units at the end, so I know where I'm going. We're going to take our given and put it as the first thing on our line. They gave us 5 grams of magnesium, so I'll put that as the first thing on the top of my line. Now I need to get from grams of magnesium to grams of MgO. It's really tempting to write MgO as just OMG every single time, but that wouldn't be chemically correct because the cation always needs to go first. But oh my gosh, it would be great if we could do that. I'm going to set up the skeleton pattern that you will see anytime you go from grams to grams. So if we're going from grams of Mg to grams of MgO, we first need to get rid of grams of Mg. The only way we can do that is by using our molar mass. Just like from our graphic organizer on the previous couple slides, if we're going from mass to an amount to a mole, we have to use molar mass. So the first thing we're going to do is figure out the molar mass of magnesium, and that's our grams per mole. This way, our grams of magnesium will cancel. Well, shucks, if I do that, then I still have moles of magnesium, which does not equal our goal units. This is where the mole ratio comes in handy, because now we can get rid of the moles of magnesium and have moles of MgO on top. Our goal always goes on top. So herein is my mole ratio. I have moles of MgO over moles of magnesium. Where am I going to find those numbers? The balanced chemical equation, of course. So this is where I would take my 2 from MgO, put it here, and my 2 from Mg, and put it there, our mole ratio. But notice, now I have the right chemical, I have MgO, but I still need to get to grams. So again, anytime I need to go from moles to grams, I'm going to use molar mass. So now I have grams of MgO per mole MgO for my molar mass. Let's go back and cancel. We'd see that our moles of magnesium would cancel here. We see that moles of magnesium oxide would cancel here. And we would in fact be left with our grams of MgO. So we know we've set it up correctly. So before we plug in the rest of the numbers, take note of the pattern you see here. We have, and this is the pattern that will always be forever and always when you're given grams of one thing and you're finding grams of another. You're always going to start with your given as usual. You're going to have your molar mass of the given. You're going to have your mole ratio, where your goal chemical will be on top, because your goal always goes on top. And then you'll have your molar mass of your goal chemical. This will always be the same pattern you witness every single time. All right, so for the molar masses of our magnesium and magnesium oxide, we just need to look at our periodic table. For magnesium, that was the 24.305 per 1 mole of magnesium. And conveniently, we already calculated magnesium oxide's molar mass in the quick review at the start of the video. And that, if you remember, was 40.305 grams of MgO per 1 mole of MgO. Now all we have to do is plug and chug into our calculator. The whole top has a bunch of numbers you're going to multiply together, and the bottom has a few numbers you need to multiply together. And then you're going to take the top and divide it by the bottom. So we have 5 grams times 1 times 2 times 40.305. Let's figure out what that is first. When I hit enter on multiplying all those values together, I get 403.05 for my top. Now I need to figure out the bottom. The bottom has 24.305 times 2 times 1. Let's plug that into our calculator. And when I do that, I get a value of 48.61. Now when I divide my 403.05 divided by 48.61, I get 8.2915 grams of magnesium oxide. Whoa! So literally, if you took 5 grams of magnesium, you would create 8.2915 grams of magnesium oxide in a perfect world. Now that we've tried one together, go ahead and pause the video now so you can try it too. Just like before, we're going to take our 5 grams of oxygen as our given and put it as the first thing on our magical line to freedom. Notice I've already set it up for you with the equal sign, the space, and our goal units of grams of MgO. Aren't I nice? I set it up for you. Oh. Okay, so 5 grams of oxygen, and I'm going to label everything because labeling is muy importante in this stage of chemistry. We have 5 grams of oxygen to start. We need to get from grams of oxygen to grams of MgO, a different chemical. Since we're noticing we have 2 different chemicals, we're going to use our same pattern. Given, molar mass, mole ratio, molar mass. Answer! So, we need the molar mass of O2. Where do we find that? On the periodic table. We need to find oxygen's mass and multiply it by 2. Oxygen has 16 mass per atom times 2. Gives us a value of 32 grams per mole. Now, in order to get rid of the grams from our given, we need to plug the 32 grams on the bottom of our next domino piece. So we're going to have 32 grams of O2 in 1 mole of O2. Now is our mole ratio. In our balanced chemical equation, we see that there is a 1 in front of the oxygen, and there is a 2 in front of the magnesium oxide, which is the product. The product is our goal. That's where we're going. And the goal goes on top. So here we would put our 2 moles of MgO on top, and we would put our 1 mole of oxygen on the bottom. We have to do that because now also our moles here will cancel. Now we notice that we have the right chemical, but not the right unit. We need to still go from moles to grams of MgO. And anytime that's the case, we use our molar mass of MgO now, a different chemical. We can actually use the same molar mass we've again already calculated from the quick review, which happened to be 40.305 grams of MgO in 1 mole of MgO. Now we can see that moles of MgO cancels, and I am in fact left with my goal unit, so I know I set it up right. Now I can plug and chug into my calculator.
Few moments later.
So when I divide those two values, I get 12.595 grams of MgO. Whoa, wait a second. So I took 5 grams of oxygen and I got 12.595 grams of product from that? That's really interesting, don't you think? In both of these problems, we used 5 grams of each reactant. to create a certain amount of product. So we did two different dimensional analysis setups where we said, okay, if I had 5 grams of magnesium as a reactant, or I have the same amount, 5 grams of oxygen as a reactant, how much magnesium oxide product can I make? Based off of our previous calculations, which reactant created more magnesium oxide product? Think about it. Why do you think that's the case? Hopefully you remember that with magnesium, 5 grams of magnesium, you were able to make 8.2 something grams of MgO. Whereas with 5 grams of oxygen, you were able to make 12.595 grams of MgO. So right away, using the same amount of either reactant, you actually you created more product from the oxygen, from using 5 grams of the oxygen. Mathematically speaking here, it's because oxygen has 2 atoms present. Go back and look at the video and try and figure out why mathematically you end up with more product of magnesium oxide using 5 grams of oxygen as opposed to 5 grams of magnesium. And think about how this is applicable in real-world chemistry. What kind of implications does this mean for chemical experiments and laboratories all around the world? Let's try one more practice question before you test yourself, before you wreck yourself. If you were to mix bleach, which never ever do this, it's dangerous. It can create chloramine gas, which is a dangerous lung toxin and can make you very, very sick and even cause death. So don't do this, please. But if you were to mix bleach, which is sodium hypochlorite, NaClO, with ammonia, it forms chloramine and sodium hydroxide. If I wanted to know how many grams of bleach would be required in order to create 12 grams of this really horrible chloramine gas, I could do my dimensional analysis setup to figure that out. First, I need to have my balanced chemical equation, obviously, from the words here, so I know what my mole ratios will be. So first, we'd have to write out NaClO plus NH3, which is my ammonia, reacts to form, that's our reaction arrow, NH2Cl, which is our chloramine gas, and NaOH, sodium hydroxide. So before we do any dimensional analysis setup, we need to balance this chemical equation first. Let's double check. We've got one Na here and one Na here from product and reactant side. We have one O here and one O here. That checks out. We have a chlorine here and a chlorine here. That also checks out. We have one N and one N here. That also works. How about the H's? I have 2 plus 1 for 3 on the product side, and I have 3 on the reactant side. Wow, this chemical equation's already balanced. But notice that I didn't move forward until I double checked that. Because if it's not balanced, your entire math setup is pointless. Now I can draw my magical line to freedom. Put my equal sign in a space for my answer. Here, my goal is to find grams of bleach, which is that one. How many grams of NaClO would be needed in order to create my 12 grams of chloramine gas, which is that one? That's my given. So 12 grams of NH2Cl. I'm going from grams of one chemical to grams of a different one, so I know I'm going to use the given molar mass, mole ratio, molar mass pattern just as before. So first I need to find the molar mass of my NH2Cl. If we look at our periodic table, we'll find that nitrogen has 14.007 mass, plus 2 hydrogens, that's 1.008 times 2, plus every chlorine has 35.45 mass. Let's add all those up together to find the molar mass of NH2Cl. When I do that math, I get 51.473 grams of NH2Cl in 1 mole of NH2Cl. Notice I haven't skimped on my labeling. Now my grams of NH2Cl will cancel, and I need to get from mole of the NH2Cl to mole of NaClO. Remember that our balanced equation had ones in front of every single one of these because it was already balanced. So here I have 1 mole of NH2Cl from here, and that is equivalent to 1 mole of NaClO, my bleach. Now we can see that my moles of NH2Cl cancel, and I'm left with moles of NaClO, which is the correct chemical, but the wrong unit. Now I just need to find the molar mass of NaClO in order to get to grams. We would look at our periodic table and see that each Na weighs 22.99, plus each Cl weighs 35.45, plus each oxygen weighs 16. Let's add those three values together for the molar mass of NaClO. And my mass happens to be 74.44 grams of NaClO in 1 mole of NaClO. Now we see that the moles cancel of NaClO, and I am indeed left with my goal units, so now it's just a matter of plugging and chugging in my calculator.
Much later.
And my final answer, drumroll please, is 17.35 grams of bleach. So if I wanted to make 12 grams of chloramine deadly gas, I would need 17.35 grams of NaClO. Now is the time to check yourself before you wreck yourself. So before you move on to part 2 of mole ratios, make sure that you give this question a try. How many grams of iron 3 oxide, that's our product, could be produced using 4 grams of iron, this reactant? Make sure you balance that chemical equation before you do any calculating whatsoever. I hope this helps your understanding of mole ratios. Give me a quacks up, and that's all for today, ducklings. Have a ducky day.
No ducks, no glory.